Hello everyone, my name is Zhen Xiang. I'm currently a postdoc at University of Illinois Urbana-Champaign. Today I'm going to talk about MMBD, post-training detection of backdoor attacks with arbitrary backdoor pattern types using a maximum margin statistic. This work was done when I was a PhD student at Pennsylvania State University. I was very honored to work with Han Wang, who has already graduated now, and my PhD advisors, Professor David J. Miller and Professor George Cassidis. Han Wang, Professor David J. Miller, and Professor George Cassidis are also affiliated with Anomaly Inc. I'll first introduce some backgrounds on backdoor attacks and defenses. I will then talk about our backdoor detection approach using max margin, and then our backdoor mitigation approach with neural activation bound. And finally, I will talk about conclusions and the broader impacts of our work. And note that backdoor mitigation here is a follow-up step for backdoor detection that cures the models being infected, which is very important. That's why in our title, we call it backdoor detection, but in our work, we have two parts, one for backdoor detection and the other for backdoor mitigation. So what is a backdoor attack? A backdoor attack is also called a Trojan attack, which is usually specified by a source class, a target class, and a backdoor trigger, also known as a backdoor pattern. The adversarial goals are twofold. First, if a test sample from the source class contains the trigger, then the model is supposed to misclassify it to the target class. But for clean test samples without the trigger, the model is supposed to correctly recognize them. Here we consider an example of an image classifier designed to recognize different traffic signs. The source class can be stop sign, the target class can be speed limit sign, and the backdoor trigger can be a yellow box that can be physically implemented, for example, using a yellow sticker. And the first adversarial goal basically says, if there's a yellow square on the stop sign, then let's misclassify it to the speed limit sign. And this can be catastrophic. For example, for applications like autonomous driving, a backdoor attack like this will possibly lead to a traffic accident. And the second adversarial goal says that for clean stop signs without this yellow box, let's just correctly recognize it. And this second goal makes backdoor attack very stealthy because it will not be easily detected, for example, using validation accuracy. In many cases, backdoor attacks are launched by poisoning the training set of the model. The adversary will first collect some stop sign images, embedding the backdoor trigger, and then misclassify them, relabel them to the speed limit sign. And these created samples are inserted into the training set for backdoor poisoning. So the model will learn the mapping from the source class to the target class when there is a trigger in the input. And recently, backdoor attacks can also be launched by directly manipulating the model parameters. So this is backdoor attack. And what about backdoor defense? In this work, we consider a very challenging post-training backdoor defense scenario where the defender is assumed as a downstream user of the model, wants to know if the model is good to use or not, or some third-party inspectors, for example, a government official who wants to know if the model is safe to deploy or not. The goal for backdoor detection is to infer if a given model is backdoored or not. That is, given any model to be inspected, a backdoor detector can be viewed as a binary classifier with two potential outcomes, backdoor or benign. And the goal for backdoor mitigation is to remove the backdoors from infected model. That is to give us a benign model without backdoor mapping, but with very high performance on benign samples. And usually, for backdoor detection and mitigation, the defender is assumed with some benign samples to complete the task. But note that in our detection work, we will relieve this assumption. So our detector will not need any benign samples for detection, which is one of the major advantages of our approach. In practice, post-training backdoor defense is very challenging, especially for the backdoor detection. First, there will be no benign models for reference, for example, to set a detection threshold. And more importantly, the defender will have no access to the training set, so there will be no prior knowledge about the backdoor trigger. But unfortunately, there are a lot of different trigger types on the market. For example, for images, the trigger can be an image patch, the trigger can be some noisy pattern that can be added to an image. For natural language, the trigger can be some trigger words. For audio signal, the trigger can be inserted wavelet. For point cloud, the trigger can be inserted points, and for image or videos, it could be some blended image frames. So the question is, how can we detect and mitigate backdoor attacks regardless of the trigger type? So in the first, I'm going to talk about our backdoor detection approach using our novel maximum margin statistic. The key idea of our approach is to cast the detection problem into a statistical hypothesis test. Okay, so for statistical hypothesis test, we will use some significance level instead of some hard threshold on statistics, which may not be scalable to other datasets or models. And we want to leverage general hypothesis independent of the trigger type. So informally, our hypothesis is based on an observation that a common trigger will be embedded in a sufficient number of examples, so the backdoor mapping will be well learned. For example, here we have the same trigger embedded in a large number of different images. And even for the so-called sample-specific backdoor trigger that exhibit different patterns in a pixel domain, they will share a common feature in the internal layer of the neural network. In contrast, the class discriminant features typically exhibit very high variability, so these two effects together will lead to an overfitting to the trigger. But now the question is, how do we quantify such an overfitting? Recall that a backdoor mapping will lead to a prediction to the target class when there's a backdoor trigger. So the signature of the trigger overfitting will be some differences on the landscape of the model's mapping from input to the output. First, the maximum achievable logic for the backdoor target class will be boosted if there's a backdoor attack. And the logic here means the model output just before the softmax. And the corresponding logic over all the other classes will be depressed. These two together leads to an abnormally large max margin for the backdoor target class. And max margin is our detection statistic here, which can be formalized as the following. Now we suppose there is a backdoor attack with some target class T. The left-hand side of this inequality is the max margin for the target class T, and the right-hand side is the max margin for all the other classes C. Okay. And if we take a closer look at the left-hand side, we'll have the first class to be the target class logic, and the second term to be the maximum logic over all the other classes, and their difference is the margin. And here we want to maximize this margin over the entire input space denoted by this calligraphic X. So that's why we call this statistics a maximum margin statistic. You can observe that during the computation of max margin, we will not need any clean samples because our maximization is over the entire input space. Okay? And note that if there's a backdoor attack, we'll have the left-hand side to be much larger than the right-hand side. And this will lead to our two-step detection procedure. In the first step, we compute a max margin statistic for each class by solving the following problem with some random initialization, for example, some random noise in the input space. And again, we do not need any benign samples to compute max margin or for the rest of detection procedure. In the second step, we compute an order statistic p-value with reference to some null distribution, for example, a gamma distribution for positive statistics, and then we compare it with some prescribed significance level, for example, the classical 0.05 for hypothesis test. The reason why we use order statistic p-value is because we want our detector to be scalable to a large number of classes, for example, ImageNet with 1,000 classes. Okay, so this is our detection procedure. Before going to the experiments, let's take a look at a toy example on 2D to better understand the max margin statistic. Here we have training examples from 3 classes on 2-dimensional space. We have some inserted backdoor training examples represented by the green cross with the target class being class 3. Now we plot the margin function for each of the 3 classes, and we observe that the maximum of the margin function for class 3 will be much larger than the other 2 classes. Now, if we increase the number of samples, used for backdoor poisoning, we will have an even larger max margin for class 3. So this tells us more backdoor training examples will lead to a larger max margin for the backdoor target class. And usually in practice, the attacker would like to have the attack to be successful. So it's very natural to insert a lot of backdoor training examples to ensure the success of the attack. And this will make the attack easier to detect. In our experiments, we consider several different types of backdoor triggers very popular on the market. And we compare our method with several baselines of 4 different datasets. Here we show the detection accuracy of our method on benign models and backdoor models, and the detection accuracy on backdoor models is average over all those different types of backdoor trigger types. And we show that in general, our method achieves higher detection accuracy than the other baselines with low false detection rate, showing the effectiveness of our method. And usually for these baselines, they're just designed for a particular or a subset of backdoor trigger types. That's why they sometimes achieve very low detection accuracy, the average detection accuracy. We also show the performance of our backdoor detector for other data domains, for example, speech signal and point cloud. Here we train 10 benign models and 10 backdoor models for each data domain. And our attacks are very successful with high attack success rate and a very small degradation in the benign accuracy. And we show that our method, our detection method, achieves high detection accuracy on these 2 data domains. Okay. So now let's take a look at our backdoor mitigation approach with this neural activation bound. Our method is based on the key ideas that a backdoor trigger will stimulate very large neural activations in the internal layers, as shown by the figure here. The black dots are the neural activation values for a backdoor model, and the yellow dots are the neural activation for benign models. Okay, so this will directly lead to a mitigation approach that is to set an upper bound on the neural activation, which will constrain the neural activation for those backdoor examples. And you can note that by applying this upper bound, we will not need to change any of the model parameters. So how do we achieve this? Here we denote the logic function without the activation bound as GCX. And now, if there's activation bound denoted by Z's, we will have the logic function being denoted as the following with a bar on the GC. And our neural activation bound is optimized by solving the following optimization problem. We want to minimize the neural activation bound to block some large stimulations of neurons corresponding to backdoor triggers without sacrifice in the model utility. That is, we want to set a constraint such that the model performance on benign samples will not be dropped clearly. And this problem will be solved using a surrogate based on Lagrangian using gradient descent. Okay. So the performance of our method is very effective. We compare with some baseline mitigation approaches, and we can see that in most of the cases, our method reduces the attack success rate with a very small degradation in the benign accuracy of the model. And we observe that there are some failure cases on the chessboard, the chessboard pattern, which is very subtle, and it's possible for our method to be combined with other mitigation approaches because our method does not change the model parameters, and we can use other fine-tuning based method and then apply our neural activation upper bound. And our follow-up works that involves the inference based on a real-time test input, this performance will be further improved. Okay. So in today's presentation, I've talked about MBD, which is a backdoor detector that does not depend on the trigger type. And we use a novel max margin statistic for detection. and we don't need any benign samples for detection. We also introduced the MMBM, which is a backdoor mitigation approach based on optimized neural activation bound with the follow-up work to be even stronger. Here, we show the impact of our work. We have used our MMBD and MMBM in the first children removal competition affiliated with NeurIPS 2022, and we have achieved the second place. And notably, our method achieves very high PACC, which is the classification accuracy on those samples embedded with the trigger. But we want to infer the originally source class of those samples with the trigger. So our method is not only novel in the methodology part, it's also very effective as shown by our achievement in the competition. So this is the end of my presentation, and any questions can be emailed to this address here. And thank you.